Okay, so let's take a look at problem number 2. I find related rates problems are a little bit trickier than optimization. This is a tricky problem because in this problem, the variables and the rates are not quite clear. It's not clear what exactly the variables are and what the rates are. Defining your variables is going to be crucial. This was a problem from last year's summative, and I believe I would say about 80 to 90% of people had trouble making any progress on this question. And I think the reason for that was they didn't define their variables clearly. Okay, so I'm going to go over how to do that in this video. Hopefully it's helpful. Okay, so it says you're on a Ferris wheel revolving at 3 radians per minute. So you're revolving at a constant rate. Okay, so let me just make a note of that. This is constant. So what that means is for each minute that passes, you kind of travel 3 radians. Okay, so 1 minute passes, you travel 3 radians, then another 3 radians, and then so on. For those of you in physics, that's your angular velocity. For those of you who are non-physics, it's not really that important, but I thought I'd mention it anyway. Okay, so it says, how fast are you going vertically upwards? Okay, so they use this. It's not ambiguous, but it's also not clear. They want you to figure out how fast you're going vertically upwards, whatever that means, when you are at point A. So this is point A here. And point A is 6 meters above the center of the wheel. So this value is going to be important. The 6 meters above the center of the wheel. This is kind of the instant at which you're finding the rates. Okay. So I want to make it clear that this value here is not a constant, okay? Meaning the 6 meters above the center of the wheel, it's not always, okay, so this is not a constant. This is just the particular instant in time at which you're evaluating your related rate equation, okay? Because obviously the height above the center is not always going to be 6 meters. Maybe it'll be 6 meters, 0 meters, negative something meters, 10 meters here. So that's always changing. It's just that we're interested in finding a rate when the height above the center of the wheel is 6 meters. So this height seems to be important, and we're gonna have to use this height measurement somehow. So when you define your variables, you want to keep that in mind. You want to keep in mind that like this height that they're providing you above the center of the wheel is going to be important. Okay, so how do we do this? How do we solve the problem? The key to solving this problem is clearly defining your variables, okay? And they don't give you that. That's what makes this problem tricky. All they give you is the rate at which the angle is changing. So we know the angle with respect to time is increasing at 3 radians per minute for each minute that passes. Okay, so we definitely know that the rate at which the angle is changing is increasing at this rate, but they don't even give you the angle. So where is the angle being measured from? And this is one of those cases where you kind of have a little bit of freedom over where you define the angle from. But I would argue that some ways of defining it are better than others. So I'm gonna define this to be the horizontal. And what we're gonna do is we're gonna measure theta, our angle, from the horizontal that passes through the center of the wheel counterclockwise, in the counterclockwise direction. Okay, now there's so many different angles. You could define an angle this way, you could define an angle in a different direction, like clockwise, but whatever choices you make, you have to write them down. So I'm going to say let theta, and theta here is going to be implicitly a function of time, because as time passes, you're kind of revolving at a constant rate. Okay, so theta, which is implicitly a function of time, is the angle measured from the horizontal counterclockwise, okay? Or in the counterclockwise direction, you can also say. I would say last year, the students who wrote this line down and the next line underneath, the students who defined the variables clearly, they scored full points on this problem. And then the students who did not define the variables would either score no points or would make very little progress. I can't stress to you how important it is to define your variables clearly. It really helps set up the problem, okay? Okay, now the next thing, we somehow need a notion of how fast we're going vertically upwards. So I'm going to call the vertically upwards part, so vertically upwards. So we need some notion of a rate that represents vertically upwards. I'm going to call that dH by dt. Okay, so this here represents your angular rate. Okay, so this is rate at which the angle is changing. But we don't just need that. We also need some notion of how fast the height is increasing. Now, there are different ways you can measure the height. You can measure the height from, I don't know, from the ground up to point A. Okay, so that's one way to measure height. Another way could be you measure height from the point A above the horizontal. That's another way to measure height. Now, in this case, that's going to be the better way to measure height. And the reason is because, look, they're giving you a piece of information here. And this piece of information is kind of like a hint as to how height should be measured. So we know that point A is 6 meters above the center. We have no clue what this distance is. So it makes sense to measure height above the center, above the horizontal. Okay, so I'm going to call that h. And I'm going to say let h, and the height is also implicitly a function of time. Let h of t be the height above the horizontal, okay? As soon as you define those two variables, it becomes clear how you have to proceed, okay? But defining the variables is so important. Okay, we know how we need to proceed. We need to somehow find this rate, dH by dt. Before we do that, we need an equation that relates the height to this angle. We can see that it's a right triangle. We can see the hypotenuse is fixed, okay? And so we know that we're going to need a trigonometric equation. The trigonometric equation that relates the opposite side, or the y-coordinate, to the hypotenuse, the radius, is going to be sine. Okay, so we're going to say sine of theta is going to be the ratio of the opposite side, or the y-coordinate, to the radius. Okay, so that's going to be h divided by t, 10. Okay, the next thing we're going to do, it might be nice just to multiply through by 10, okay? And if we multiply through by 10 and rearrange, we get h equals 10 sine theta. The reason I do this is because we're interested in this rate, the rate at which the height is changing. So it's nice to kind of isolate for h here, although you don't have to. The next thing we're going to do is we're going to take the derivative with respect to time. You'll see this is very common for related rate problems. You always want to be implicitly differentiating with respect to time. On the left, we get a rate. The rate we get on the left is dH by dt. Remember, h is a variable, and h is implicitly a function of time. On the right, you got to be careful. This 10 you can pull out, okay? So that 10's not going to do anything. But here you got to be careful. So here, sine of theta. Here you have a situation where you have an outside function, sine, and then an inside function, which itself is a function of time. Okay, so take the derivative of the outside function, leave the inside alone. So that's going to be cosine theta, and then multiply by the derivative with respect to time of the inside function. So that's going to be d theta by dt. Okay. Okay. So what this related rates is saying is these two rates are related. The rate at which the Ferris wheel, your height is increasing vertically upwards, is somehow related to the rate at which the Ferris wheel revolves, and also where you are on the Ferris wheel, at least in terms of your angular position. Okay, so what we need to do is find this, and we need to find this at a specific instant in time. The instant in time we're interested in is... we want the instant in time when we are 6 meters above the center of the wheel. Okay, so what we want is the rate when h is 6. Okay, so this is where I'll make a second drawing. So the second drawing, maybe h is 6 meters. The radius is 10 meters. And because of because this is also one of your special triangles actually. So this is the 3, 4, 5 triangle scaled up by 2. So this length here is going to be 8 meters. Okay, but you can also use Pythagoras' theorem if you like. Okay, so the cosine of theta, let's say this is theta, the cosine of theta, you can kind of see like this is constant, and this thing you can find using the triangle. Okay, so we can say when h is equal to 6 meters, so now I'm evaluating at a particular instant in time, the instant in time when the height is 6 meters. When the height is 6 meters, cosine of theta, it's clear from the drawing, is going to be 8 divided by 10, which is 4 divided by 5. Okay, and d theta by dt is fixed, it's constant, it's always 3 radians per minute. Okay, is it per minute? Let's just confirm. Yeah, 3 radians per minute. Okay, so that's it. We just need to evaluate now. So we get dh by dt is equal to 10 times the cosine of theta, which is 4/5 when h is 6 meters. Oops. And then multiplied by d theta by dt. Okay, and d theta by dt is constant. It's just 3. Okay, so if we simplify, we get 5 goes into 10 twice, and then we get 4 times 2 times 3. That's going to be 24. Don't forget, you're dealing with a rate and a physical rate that you need to supply units for. The units are going to be units of height, which are in meters, divided by units of time. The units of time are in minutes for us. Okay, so we get something like this. That's our final answer. Just write a concluding statement. You could say, therefore, height is increasing because the rate is positive at 24 meters per minute at this instant. Okay, the instant being the instant when the height is 6 meters. Now, if this rate was negative, okay, so if this rate were negative, it might be a case like when you're moving down, okay, like your height is decreasing from the horizontal. So yeah, it might be positive, it might be negative, okay. The sign of the rate kind of tells you which direction you're heading in. Are you heading away from the horizontal, or are you heading towards the horizontal? Okay. All right, so that's the second related problem, a related rate problem. Hopefully that makes sense. Hopefully that helped. Make sure to practice lots of questions with related rates. These problems can get tricky, okay? And the only way you get good at it is if you do enough practice. Okay, so these are some steps. These steps are just kind of general steps that you can use to help you solve related rates problems. If they're helpful, you can jot them down. But here they are. So the first is just draw a large clear diagram. That's very important. That'll help you set up the problem. As soon as you draw the clear diagram, in your mind, distinguish between what the variables are and what the constants are. The variables are typically going to be functions of time, and the constants are never going to change. Sometimes the constants are like quantities, sometimes they're rates, like, so it just depends. But just distinguish between them. The third step is recognize if your variables are implicitly a function of another variable. So usually that's going to be in terms of time. Fourth step is to somehow write an equation that relates the variables. Usually this will be an equation from geometry or from trigonometry. Fifth step is usually to implicitly differentiate with respect to time. It's almost always time. Yeah, I want to say it's always time. I've never seen a problem, at least in HL math, where the implicit you're differentiating with respect to something other than time. Okay, so it's always going to be time for us. And then sixth is just solve for the unknown rate. Okay, so hopefully these steps help. Good luck with your related rates problems.